We are really excited to welcome Abigail Metcalfe to our webinar series today. Abigail is based out of, or I'm sorry, she did her, clicking on things. She did her master's degree at Durham University and then her PhD at the Institut Physique des Globes in Paris. And now she is a postdoc at the Laboratoire Magmas des Volcans. I'm sure I just butchered that, but please excuse my pronunciation. And she's going to be talking about the Lesser Antilles Arc today. A couple of other announcements before we get rolling. The SZ4D student exchange program is still accepting applicants for another week here or so. So if you're interested in that, please fill out that form. There's also a survey for SZ4D that we have for all of our events. So please take a minute to fill that out for us as well. And I'm just going to read a quick summary of SZ4Grads and SZ4D here, and then we can get rolling. All right. SZ4Grads is a collaborative, interdisciplinary, and intercultural network for graduate students and early career researchers. And my screen froze. Sorry about the technical difficulties. Yep, I can do that, you're on. Please tell me if that survey doesn't go through. I think it should now. All right, my screen still will not load for the SZ4D intro, but we are an intercultural collaborative network of early career researchers and grad students who's interested in subduction zones and building a community around that, that kind of theme. And then SZ4D is a large interdisciplinary team of scientists from all over the world that is working to understand subduction zones and subduction zone hazards. And SZ4Grads falls under the Building Equity and Inclusion umbrella of that organization. And so with that, I'm excited to welcome Abigail to our talk today. So if you're ready to take it over, Abigail.
Great, thank you. So yeah, today I'll be presenting work that I did during my PhD, which became a review of the Lesser Antilles. So all the data presented here is from the literature and it's available online. It's compiled in the supplementary material of the paper, which is in Science Reviews. And I'll be focusing on the geochemistry, magma storage, and eruptive styles. So the Lesser Antilles is an active volcanic arc in the Caribbean, and it spans 850 kilometers from Saba in the north to Grenada in the south. The active arc is made up of 11 main volcanic islands and an archipelago of 19 smaller islands, which are the Grenadines. The Lesser Antilles is formed due to subduction of the North American plate beneath the Caribbean plate. And compared to other arcs, the subduction rate is slow, and this results in a low magma production rate in comparison to other subduction zones. So to the north of Martinique, the arc splits into an inactive eastern limb, which is known as the Limestone Caribs, and is inactive today. Activity on the arc has migrated westward, and this forms the Western Arc, which has been active since the early Miocene. So each island has at least one active volcanic complex, except for Dominica, which has 9 potentially active volcanoes, and Guadeloupe, which has 2 potentially active volcanoes. So recent volcanism has occurred in narrow 10-kilometer wide zones which is split into 3 segments. So the first is the northern arc, which is from Saba to Montserrat. So here we have examples of St. Kitts, and here we have Soufriere Hills volcano on Montserrat, which is one of the most famous volcanoes in the Lesser Antilles. Slab dip varies along the arc and is around 50 to 60 degrees in the northern arc, and the crust here is about 30 to 37 kilometers thick. Generally, the magma is erupted tholeiitic suites, but I'll talk more about the chemistry later. We then have the central arc, which is from Guadeloupe to Martinique. So we have La Soufriere de Guadeloupe, the Morne-Plat-Pays complex, which is in the south of Dominica, and then Montpellier, which is in Martinique. Again, crustal thicknesses between 30 to 37 kilometers. And the central arc has the highest magma productivity, as some of the largest eruptions have occurred in this region. In particular, on Dominica, we see large tuff deposits. So the northern and central volcanoes can produce large explosive eruptions, which generate hazards such as pyroclastic flows. They can also produce large lava domes, and these are often associated with block and ash flows after collapse. The southern arc is from St. Lucia to Grenada, and this also includes the submarine volcano of Kikumjeni. Slab dip is subvertical in the southern arc, and to the south of Martinique, the crust thins, and the crustal thickness here is estimated between 20 and 30 kilometers. In the southern arc, we see stratovolcanoes, small explosion craters, and lava flows. Large dome-forming eruptions are a lot rarer, and this is due to a change in magma chemistry, as the southern arc suites are silica undersaturated and highly magnesian. So I'll move on now to the eruptive history of the arc. So this is from 1900 to present day, and we have the islands which have had eruptions. And we have the different type of eruptions, which range from small phreatic to effusive dome forming to large explosive eruptions. And for each eruption, we have the main eruption style, the eruption length, and the eruption phase in the case of Montserrat. I've also indicated the main volcanic explosive index where applicable, and also the average bulk rock, SiO2. So 23 eruptions have occurred in the Lesser Antilles since 1900. And the most common eruption style is submarine eruptions, and this is due to the high level of activity observed at Kikumjeni. So multi-phase and transitional behavior is very common at volcanoes in the Lesser Antilles, and eruptions will often transition from non-magmatic to effusive to explosive behavior. Smaller and less explosive eruptions are more common. For example, phreatic eruptions, which are non-magmatic eruptions generally generated from a hydrothermal system. Small Vulcanian explosions and effusive dome eruptions are also common. However, we also see more explosive activity with subplinian and plinian eruptions recorded. Two of the most devastating eruptions occurred in 1902, one on Martinique and one on St. Vincent. Both of these were multi-phase eruptions and had phases of effusive dome building, phreatic eruptions, and also lateral blasts recorded in the case of Martinique. In more recent years, we've seen eruptions from Montserrat. So Soufriere Hills volcano started erupting in 1995, and then we also had St. Vincent in 2021. So these eruptions have resulted in the short and long-term displacement of thousands of people, which has had long-lasting socio-economic impacts. So approximately 1 million people are threatened by the direct effect of volcanic activity in the Lesser Antilles, and then 2.5 million people are threatened by the related phenomena. So to go into a bit more detail on some of these eruptions. So Soufriere Hills volcano in Montserrat has experienced a long period of eruptive activity, which began in 1995. So this eruption had 5 main phases of activity, which became increasingly more vigorous. And this included phreatic behavior, dome growth and collapse cycles, and Vulcanian to subplinian explosions. And here we just have some examples of the dynamics of the explosions that were observed. And so this eruption has provided us great insight into a range of processes such as growth and collapse of andesite lava domes, dynamics of lateral blasts and Vulcanian explosions, as well as subsurface processes and structure of the system, and also the cyclicity of magma transport linked with ground deformation. So the eruption has not been declared to be over officially, though the last major explosive event was in 2010. So seismic activity, gas emissions, and deformation must all return to substantially lower levels than have been observed so far before the eruption can be declared to be over. And most importantly, this eruption has had major socio-economic impacts for Montserrat. More than 6,000 people were evacuated during the eruption, and only 1,000 people have been able to return. More recently, we had the eruption of Soufriere St. Vincent. So this eruption began with an effusive phase in 2020 with 3 months of lava dome growth. This was accompanied by increasing seismicity, and this allowed rapid evacuations of people to happen at the beginning of April when seismic activity peaked. And this was just before the onset of explosive activity. So this began as small Vulcanian explosions and then transitioned to subplinian activity. So we can see here some examples of the eruption columns that were observed. 32 identifiable explosions occurred between the 9th and the 22nd of April 2021, and these gradually decreased in frequency and energy. There were no casualties from this eruption, and in March 2022, the plume chemistry had returned to pre-eruption conditions and the eruption was declared to be over. So we have some now examples of phreatic and effusive eruptions, which are also very common. So volcanoes on Martinique, St. Vincent, Montserrat, and Guadeloupe have lava domes or have experienced lava dome growth and collapse cycles in their recent history. So here we have a lava dome from the recent eruption of St. Vincent. This lava dome transitioned into explosive activity, but in 1971, Soufriere St. Vincent experienced a period of purely effusive activity, which didn't lead on to anything more. However, Soufriere Hills on Montserrat showed cyclic dome growth and collapse, which resulted in block and ash flows, and also ash columns, which presented a significant hazard. So moving on to phreatic eruptions, here we have the Boiling Lake, which is in the Valley of Desolation in Dominica, and it's one of the most active centers on Dominica. Vigorous hydrothermal activity is observed here, and considerable water level and temperature variations of the boiling lake are observed. A phreatic eruption was recorded here in 1997, but it was very small magnitude and had very little to no impact on the population of Dominica. In comparison, we have the 1976 to 1977 phreatic eruptions of Soufriere de Guadeloupe, which is here. So we have the Soufriere de Guadeloupe dome, which was in place during the last magmatic eruption, and then we can see the phreatic plume erupting there. So this eruption had major socio-economic impacts. More than 70,000 people were evacuated during this eruption, and there's a lot of controversy surrounding the management and decisions made during this eruption. And it really shows the impact that even a relatively small non-magmatic eruption can have. So it's had a lasting influence on the population of Guadeloupe, and it really highlights the need for clear, effective, and efficient crisis response management, even with a small non-magmatic eruption. So now we've talked about the surface expression of the magmatism. I'll move on to the subsurface. So a crystal mush system is often used to describe the chemical and dynamic features of the magmatic systems of the Lesser Antilles. A mush system is considered to be vertically extensive, and they form from repeated intrusions at depth, and they consist of melt-rich lenses and crystals, which we can see here. This is a subsolidus system, So it can exist for long time scales before remobilization, and this generally occurs through the injection of hot mafic magma from the base of the system. So many systems have had mush systems proposed for them along the arc. So here we just have a few examples. We have Soufriere Hills on Montserrat, Kikamjeni, and Soufriere de Guadeloupe. Generally, these models all include a deep basaltic component which feeds and recharges the system. We then have a main mush zone here, which is generally more basaltic to andesitic and includes exolved fluids and varying amounts of melt. And then as we move up through the system, generally we see an increase in silica content, and the systems are often described to have a silicic cap with silicic melts accumulating at the shallowest depths, which we can see in some of these models here. Above the magmatic system is often a hydrothermal system, which is fed by heat and fluids from the magmatic system. And eruptions are generally produced through destabilization of the mush system due to the arrival of a mafic magma, which releases heat and volatiles into the system and can result in processes such as mixing and remobilization of magmas stored there. And so we calculate the conditions of the mush systems in different ways across the arc. For example, some studies use melt inclusions, some studies use thermobarometry of xenoliths, some use equilibrium experiments. Seismicity can also provide great insights into the depths of the magmatic system and where magma injection is occurring. So for example, in the Soufriere St. Vincent 2021 eruption, seismicity at around 6 kilometers depth was interpreted as magma injection occurring around 6 kilometers. So however, the pressures that are determined from different methods introduce errors. So for example, the pressures determined by melt inclusions are considered minimum estimates, and I'll talk a little bit more about that in the geochemistry section. And then additionally, crystal density affects depth pressure conversions, and the crystal density varies across the arc, and the value different studies use also varies quite considerably. So here we have the bathymetry of the Lesser Antilles, and then we have the depth and then the crustal structure for each island, and then superimposed over this we have the proposed storage regions for each system, which are reported in the literature. So taking all the various storage models across the arc, we can then hypothesize that there are generally 3 levels of mush storage, which vary in depth across the northern, central, and southern arcs. So generally we have a lower crustal region, which is greater than 18 kilometers. Material from this level is very rarely observed, so it's unclear whether this is applicable across the arc or how much it varies. However, at St. Kitts, Guadeloupe, and St. Lucia, we get a good estimation for the deepest part of the Antilles system. Above this, we have a mid-crustal zone, which is around 10 to 18 kilometers. This is where basalts to basaltic andesite magmas are generally reported to be stored. And here we'd perhaps expect to see processes such as fractional crystallization and magma mixing. The most well-defined part of the magma system is generally the shallow storage zone, which is above 10 kilometers depth. So this zone is fed and remobilized from the lower zones, and the shallow area of the system contains the most evolved magmas, and these are often described to be homogeneous. Evolved magmas are reported to extend down to the mid-crust in the northern arc, but in the central arc it's pretty consistent. 6 to 9 kilometers is where the evolved magmas are being stored. So now I'll move on to talk a little bit about the magma chemistry. So for the Lesser Antilles arc, there's a large amount of melt inclusion data available. So here are some melt inclusions from La Soufriere de Guadeloupe. So under the microscope, we see the melt inclusions are the brown blobs. And then here in a SEM image, they're the dark gray blobs. So these are droplets of melt which become trapped in the crystal as the crystal grows. They are a closed system, so theoretically they preserve the melt's original composition. However, they can undergo significant post-entrapment modifications, which changes their composition. So, for example, water can be lost through hydrogen diffusion through the host mineral, CO2 can be lost to vapor bubbles, and post-entrapment crystallization can occur. So the majority of studies in the Lesser Antilles have avoided or discarded melt inclusions with obvious signs of post-entrapment crystallization or performed checks to ensure this is minimal. And then melt inclusions with bubbles or fractures are generally not analysed. So this means we can be reasonably confident that the melt inclusions in the Lesser Antilles provide a good preservation of the original major element and volatile compositions. So here we have the Lesser Antilles Islands, and then we have silica and total alkalis. And this is data from the Northern Arc. So overall, we see melt inclusion silica increasing from Saba in the very north to Montserrat towards the Central Arc. Total alkalis are more consistent, but we do see a large jump when we reach Montserrat. So the Soufriere Hills magmas have the highest total alkali contents observed across the whole arc. Moving to the Central Arc, which here also includes St. Lucia. So seismically, St. Lucia fits into the Southern Arc, but geochemically it fits better into the Central Arc. So melt inclusions here are very evolved. There is a general increase in total alkalis from Guadeloupe to St. Lucia, but this may be a sampling issue as many more inclusions have been analysed from Guadeloupe and Dominica. Guadeloupe spans the widest range of compositions, and this is because this data set includes melt inclusions from a basalt, which is a hypothesized parental magma of the more evolved melts. This is also the least differentiated melt reported in the Central Arc. The Southern Arc spans a wide range of compositions. The St. Vincent melt inclusions are more comparable to those from the Central Arc and span a similar range to the melt inclusions from Guadeloupe. And then Kikum-Jenny also has quite a wide range of compositions observed, and this could be related to the evolution in magma composition, which has been observed to change from basalt to basaltic andesite. And these also extend to relatively unevolved compositions. Grenada has the least evolved compositions and is considered to be one of the most primitive magmas of the Lesser Antilles Arc. And so overall, we see the most evolved magmas erupted in the Central Arc, and we see the most primitive magmas in the Southern Arc. And there is a potential bias in the data set as few examples of the parental and primitive magmas are erupted, so aren't analysed. And all the data here is available in the literature and is compiled in the supplementary information of this review paper, and you can scan the QR code if you want to see more of the data. So moving away from melt inclusions, here we have a compilation of the whole rock data for the arc. So we have calcium over aluminium against iron over magnesium, and we have all the different suites from across the arc. So the Grenada magmas are the most primitive and are particularly silica poor and could represent a potential parental magma composition. So using the Grenada composition, we have modeled 2 fractional crystallization paths using melts. And if you want more of the methods on that, please scan the QR code and look at the paper. But using these fractional crystallization paths, we can show that a magma of a Grenada composition can produce the suites of magma observed across the arc. Variation in sediment input across the arc means that the parental magma is likely to vary in trace element composition. So for example, in the Southern Arc, the incoming plate is rich in clastic detritus, and then in the north, there is a more limited sediment supply, and so it's richer in pelagic marine sediments. And then also superimposed on the fractional crystallization trend, processes of crystal contamination and magma mixing are also most likely occurring, which is creating the spread in the data. These processes are particularly reported in the central arc. So moving on to some volatile data. Volatile data is very widely reported along the arc, in particular chlorine, water, and CO2. The chlorine is lowest in the central arc and higher in the northern and southern arcs. Water is very variable across the arc, and this could be due to degassing processes which can occur prior to entrapment, or if the melt was not volatile saturated at the point of entrapment. However, we do use melt inclusion water content to determine pressures, and this means that the pressures determined by the melt inclusions are only considered minimum estimates. CO2 is also quite variable across the arc. The central arc is generally more CO2 rich, and in particular, we see a bimodal distribution in Dominica. So we see two clusters, one which is generally lower than 2000 ppm and one that is higher than about 3000 ppm. Jenny also reports some of the highest CO2 contents. However, generally in the southern arc, CO2 contents are below 1000 ppm. So as well as calculating pressures using CO2, we can also use this to look at the degassing processes versus CO2 fluxing that is occurring in the plumbing system. So again, I'm not going to go into any of the method here, but if you want to know the method behind this, please look at the paper. But we have CO2 gas, which we've calculated from the melt inclusion content versus pressure for the northern, central, and southern arcs. So the pressure versus CO2 data in the northern arc indicates that St. Kitts and Montserrat, we see CO2 decreasing with decompression of the magma across pressures of around 240 to 100 megapascals. However, melt inclusions from Estacia, we see CO2 increasing with decreasing pressure across a similar pressure range, suggesting that CO2 fluxing is a process that's occurring within the plumbing system here. In the central arc, again, we see decompression affecting the CO2 content in the majority of the melt inclusions, generally at pressures lower than 200 megapascal. However, in the Dominican melt inclusions, where we saw the bimodal distribution, we see CO2 fluxing occurring at higher pressures, so from about 375 to 150 megapascals, which is here. And then at lower pressures, again, we see generally CO2 decompression. In the southern arc, again, we see generally processes of CO2 decompression, but then in Grenada, especially, we have this increase in CO2 over decreasing pressures, which again indicates CO2 fluxing as a process which is occurring throughout the Lesser Antilles arc. So moving away from the geochemistry and more to monitoring unrest at the volcanoes. So the Lesser Antilles is very active, and there is an extensive monitoring network for many of the volcanoes. So starting with Guadeloupe, which has had only phreatic eruptions in its recent history, and the most recent was in 1976. And after this, the monitoring network of this volcano was increased to include continuous seismic and geodetic monitoring, gas plume monitoring, meteorological networks, fracture surveys, fumarole gas and thermal spring sampling, and thermal monitoring. So the volcano has experienced periods of very little activity, particularly following the last phreatic eruption. However, in 1992, activity began to increase again, and this accelerated in 2017 and peaked in 2018. So here we can see the number of seismic events per day from the beginning of 2017 through to July 2018. And we can see the number of seismic events per day accelerating through 2017 and increasing to a peak in April 2018, which was when a felt earthquake, and it was 4.1 magnitude, was felt by the population. And this was the largest seismic event since the 1976 eruption. So this episode of accelerated unrest is interpreted as a failed phreatic eruption, triggered by the ascent of heat and fluids from the deep hydrothermal and magmatic system. So though no seismic events comparable to 2018 have occurred since, continued periods of seismic swarms are recorded. So the observatory publishes weekly and monthly reports on the activity here, and these are available at this link if you want more information on the ongoing seismic swarms and the gas monitoring that is occurring there. Similarly, Martinique is also experiencing a period of unrest. So this began in late 2018. Here we have the seismic events per week from January 2019 to the beginning of this year. So in November 2020, seismic unrest began to accelerate. And this increased seismicity was interpreted as evidence for reactivation of the hydrothermal systems. The continued unrest began increasing to 2021 with an increase in volcanic seismicity. This peaked in 2021, but the volcano alert level is still yellow, which means vigilance and continued monitoring. Other signs of unrest observed, the perturbation of the hydrothermal system, which is perhaps related to the circulation of hot and pressurized fluids. Areas of degraded vegetation on the flanks of the volcano were also observed. These were pulsatory in nature and they increased and decreased in size. And finally, an area of underwater gas emission was also detected in June 2021. So as with Guadeloupe, the Observatory on Martinique also publishes weekly and monthly reports, and they're available here if you want more details on the ongoing seismicity and gas monitoring and all the unrest that is happening here. So now I'm going to try and bring together a few of the main points and observations from across the arc. So here we have the Lesser Antilles, and then we have the eruptions since 1900. So we see a range of eruption styles observed across the arc, and the eruptions are generally multi-phase events occurring over long periods. So the main drivers of the eruptions is the magmatic system. The hydrothermal systems, which are often present, can result in sealing of fractures, which can lead to phreatic eruptions and also potentially affect the ascent of magma. We can also summarize the storage regions. So we have the lower crust storage at greater than 18 kilometers, the mid-crustal zone at 10 to 18 kilometers, and then the upper crustal zone. The active region of mush within the shallow system is generally hypothesized to be remobilized by recharge from the mid-crust. The storage is not always necessarily reflected in the magma temperature from the melt inclusions. This is something that was a bit puzzling, but I think the range of magma compositions and the different methods by which the temperature is calculated really means you don't really see the storage reflected in the temperatures. And then we have the most silicic magmas in the central arc. And for the volcanoes which have been most recently active, so Montserrat, St. Vincent, the eruption products are described as having restricted bulk compositions and few systematic compositional changes. However, there is a large spread of compositions across the arc, indicating magma mixing, crystal contamination, and fractional crystallization are all processes which are affecting the compositions. We also have a wide range of water contents, which can be used in various ways to show storage depths to different processes occurring in the plumbing system. Something which I didn't talk about today yet is the melt inclusion boron data, which is available across the arc. So we see the highest boron values in the central arc, and high boron values are related to a higher supply of fluids from depth. So this suggests that the central arc has a very high supply of fluids compared to the southern and northern arc. And this is most likely related to the fracture zones subducted underneath the central arc. So the central arc has the highest silica magma, the highest magma productivity, the shallowest storage depths, and multiple volcanoes in a state of unrest. and this is most likely due to the high supply of fluids to the central arc, which clearly has had an impact on the evolution of the arc and the surface expression of volcanism today. So here are a few final conclusions. Investigating trends across the arc is useful to provide more context for each system. In the case of the Lesser Antilles, a supply of fluids to the central arc is influencing the surface expression of volcanism, particularly resulting in more evolved magmas stored at shallow depths, more explosive, larger eruptions, and the Lesser Antilles hosts multiple hazardous volcanoes, and further research should be underpinned by the effect even a small eruption can have on tens of thousands of people. There's so much exciting work that's happening on the Lesser Antilles volcanoes. Since I wrote this review, there's been so many more papers, but all the data from this paper is available in the literature, and it's a compilation of lots of different work by lots of different people. All the references are available if you scan the QR code, and that's it. It was short and hard to summarize everything, but I hope that was a good insight into the Lesser Antilles.
That was great. Thank you, Abigail. If you have a question, feel free to post it in the Q&A section or in the chat. And we've got a little bit of time for questions here. As we wait for questions to come in, I've got a quick one for you, Abigail. Where do you think the next kind of round of work is needed with your review paper? You know, where are the biggest gaps in data that we as a community should kind of work to address in the Lesser Antilles?
For me, I would say so part of the work I did for my PhD was on diffusion timescales and looking at the timescales of magma recharge. There's a lot of mineral data in the Lesser Antilles, but not so much has been done on looking at the timescales across the arc, comparing the different types of eruptions, looking at the multi-phase eruptions and comparing the different timescales there. So I would say that was definitely a huge area that can be filled.
Sure, that's great. As we're still waiting for questions, I guess I can continue to ask them. I noticed that there wasn't a ton of isotope data available besides your boron results. Have kind of typical radiogenic isotopes been done, and kind of how do they compare across the arc?
I'm not too sure about the isotope data. There is another paper, I think it's in JVGR. It came out around the same time as this that has a lot of trace element data. I'm not sure if it has isotope data in. There's definitely isotope data available for some of the southern arc volcanoes. Yeah.
Well,
may I ask a question?
please.
Hi, Abigail. Nice talk. May I ask a question about the seismicity? I think in some of your slides, you show the seismicity variations in some volcanoes, right? I see there's some temporal variations. You can see sometimes seismicity goes up and then goes down and goes up, goes down. So is this real? Or if it is real, what's the mechanism?
So this is pretty common, especially in Guadeloupe, to have these periods of seismic, they call them seismic swarms. I'm not entirely sure on the mechanism behind this. In Guadeloupe, a lot of it is related to, there's a lava dome on Guadeloupe and it's very highly fractured. And a lot of it is related to the sealing and unsealing of the fractures of the lava dome, and also the fluids injected into the hydrothermal system. That is also a big driver of the seismicity. I mean, I always feel like Guadeloupe is almost breathing. The lava dome is almost breathing with the pulsing nature of the seismicity and also the gas emissions.
Thank you.
I have another question.
Mhm.
You said that you had such a wide spread with some of your major element data and kind of attributing that to like crystal fractionalization trends and different hydrothermal fluids. And I'm curious if there's a way to kind of better constrain that to look at each process individually.
Yeah, I think for melts you can definitely also run mixing trends. For me, the issue was there's so much data, it's deciding almost what to do. Fractional crystallization was the easiest one to show the clear link between the suites. For crystal contamination and mixing, is kind of deciding what to mix with what and how much, at what temperatures, at what pressures, where in the system exactly the mixing and crystal contamination is happening is not always so clear.
That makes a lot of sense. Thank you. Definitely challenges of having too much data to model.
Yeah.
Well, if we don't have any other questions,
Yeah, I have one last question.
oh, please, thank you.
So, Abigail, I'm curious how to use geophysical methods to monitor the magma movement from the deep to the shallow.
Um, I'm definitely not a geophysicist.
Oh,
Definitely not.
sorry.
No,
Chemist.
um, in St. Vincent, it was definitely the depth of the seismicity that they were using to track the magma movements. There's definitely a lot of papers that have come out on that recently. But yeah, they were getting these high level of seismic activity at around 6 kilometers. And this was definitely interpreted as a fresh batch of magma being injected at 6 kilometers, which was then fueling the eruption.
Okay, so then how about the geochemical method?
For monitoring, it's generally through gas emissions. We look at the different ratios of the gases released to look at whether it has a more magmatic component or a more hydrothermal component. In the case where it has a more magmatic component, you would expect that magma is moving, rising, there is more magmatic gases being released. Whereas if it's a more hydrothermal signature, then you would assume there is not magma close to the surface. It's just kind of business as usual. The hydrothermal system is just pumping out gases. So yeah, definitely monitoring, looking for those changes in the gas emissions is definitely a key part of monitoring.
Okay, got you. Thanks.
Well, if we don't have any other questions, we can wrap up our webinar here. I want to thank Abigail again for being here today, and then as well as kind of advertising for our two links here, with one being the student exchange program. Please fill that out in the next week or so if you're interested. And please take a minute to fill out the survey on this event for SZ4D so we can kind of learn more about our outreach events here. So please join me in thanking Abigail again, and we hope to see you guys next week for another talk.
Great, thank you.
Okay.